Okay. Hello everyone, and in continuation to our lecture series on network theory, today we'll be doing a topic on mesh analysis. Okay. So far we have done what is KCL, we have done what is KVL, we have done what is nodal analysis. We have done a few more questions based on nodal analysis, which was strictly based on dependent sources. Today we'll begin with mesh analysis. Although we have done this and we are through with this topic for a very long time, because we have this topic in our 12th standard. But in any case, just for the sake of completion, we'll be doing this topic today. It's a very basic topic, so we'll try and know all the nuances of this topic, and then we'll move on. Okay, so let's begin. Okay, so in mesh analysis, step number one that we need to follow is find the, if whenever you're provided with any kind of circuit that you're provided. Step number one, all you need to do is find the number of meshes. Okay, you need to find the number of meshes. This is EM, sorry. Okay, okay. So first thing you will do whenever you're given with a circuit, you'll find out the number of meshes. Second, assign. What will you do? You'll assign a particular direction of current. It can be either clockwise or it could be either anti-clockwise. It is on your choice. Okay, and then in the last step, what would we do? We will write mesh equations. What are mesh equations? We'll write mesh equations using what? KVL or Ohm's law, right? So these are the three basic steps. I think you are all acquainted with these steps, right? We've been doing this even when I did not start this topic, we have been following these steps, because I believe this is what we have known. So we are through with these topics. Okay. So yesterday, when I was, leaving the class, I asked you to, study what are planar networks and how it is related with mesh analysis. So, tell me, what are planar networks? And if I say mesh analysis is applicable only for planar networks, would I make sense? See, the truth is, mesh analysis mesh analysis is strictly applicable to what? Planar networks. Okay? It is strictly applicable to what? Planar networks. Right? Now tell me, what are planar networks? A network which can be redrawn equivalently. What? It can be redrawn equivalently on a single plane. Then such a network would be called a planar network. Okay, and mesh analysis would be applicable only to what? Planar networks. Now just observe this network. Can I call it a planar network? Or in other words, can I redraw this circuit on a single plane? See, look closely to this network and tell me, this is a point which is not in the plane, otherwise everything is on the same plane. I'm sorry, there should have been a resistance here. I've skipped that resistance, but in any case, okay. See, this is what, this is a This is the only thing which does not belong to the plane, right? Right? Now see, if I redraw this circuit with something like this, is it equivalent? See, this had to be at this potential, this had to be at this potential, which is still true. This is non-touching to this branch, it is still non-touching to this branch, and now your network, which was initially what? Initially it was non-planar. You know, by the look of it, it was what? Non-planar. But when you can equivalently draw it on a single plane, when you can equivalently draw it on a single plane, in such networks, even when they are non-planar, mesh analysis would apply. Okay? See, you know, let me just put this picture for you. In such case, in such case, see, in such case, this is what? This is at potential. Let me call it as, let me call it as A and B. This is again A and B. Does anything in the network change? Let's call it C, let's call it D. Let's call it C and D. I'm inserting a resistance here, and let's again insert a resistance here. Okay. Now look closely. Just go step by step. There is a resistance between A and C in this network. There is a resistance between A and C in this network. Okay. There are two resistances between C and D. There are two resistances between C and D. Right? There is a resistance between C and B. Yes, there is. Between B and D. Yes, there is. Between A and D. Yes, there is. Now, between A and B. Yes, there is a resistance. Right? There is a resistance and it is non-touching to this branch, and now a network which was initially what? Non-planar. Which was initially what? Non-planar. When you can draw a equivalent circuit, when you can draw an equivalent circuit on a single plane, then in such cases mesh analysis would apply. Otherwise mesh analysis is what? Not applicable to such circuits. Am I clear? Okay. Now let's just see another example and let's see if this is planar or not. I am placing this circuit somewhere. I hope it's visible to everyone. Okay. Now you guys try this to redraw this circuit. Try and redraw this circuit at your home and see if you can, in any situation, can you reduce this circuit? Can you reduce this circuit to a single plane? So this is something that this is an exercise for you guys. Try and convert this network into what? A planar network. If it's possible, then what? Then mesh analysis would be applicable. Otherwise, mesh analysis will not apply. Okay, I want you to try and do it all, and tomorrow I'll, in tomorrow's lecture I'll tell you whether it's planar or not. Okay. Okay. Chalo. Now we'll just see, we'll just go through the steps of mesh analysis, and these are some basic steps that you've known so far and that you've been, even practicing before even studying this topic. You have been doing this. I have been making you solve questions based on it, but still, because you need to understand the sign convention. I am repeating this for you. Okay, it is a very basic lecture, but still, because you need to know, I am saying them loud for you. Okay. First, what did we learn in our KVL, in our steps to KVL? Tell me. The step number 1 was what? Find the number of meshes. Okay. So tell me, how many meshes do you see in this network? Can I say this is 1? Can I say this is 2? So how many meshes do you see? 2, right? Right? Okay. Tell me, do you see any other loop in this network? Okay. Is this another loop? Right? So number of loops is what? 3. Number of meshes are what? 2. Right? How many loops do we see? 1, 2 and 3. Right? Right? Okay. I'll tell you what is a mesh and what is a loop, once we find a similar question. Okay. When we're doing a question of this sort, we'll be, I'll tell you what is the difference. For now, just understand there are 2 meshes in this network and 3 loops in this network. Am I clear? Okay. Let me just clean the board for you and then we'll see. I'll tell you how sign convention is taken. If you have been making mistakes in sign convention and this is what is causing silly mistakes for you, please be very alert, and from here on you will, understand what are the different sign conventions in a network. Okay. See, uh, the first thing that you need to notice is source is not assigned any polarity because it is already assigned. Okay, so you will not assign any polarity to the source because what, it is already defined in your network, right? Okay. The second thing that you need to understand, at any point when the current is entering in any element, what will you mark it? Tell me what, at any element when the current enters, what is the sign which is assigned? The sign assigned is positive. Be very clear. The current is entering. See, this is the direction of the loop. So the current is entering from this. When it is this, what will be here? This will be positive. Fine. Point number 3. Tell me, when current is leaving element, what is the assignment of sign? Tell me. It is what? Negative. Okay? Okay? Whenever, okay? Right? Whenever whenever we are traversing from positive to negative, from positive to negative, what do we observe? We observe a drop. Something is at a higher potential, we are going to a lower potential. What will we experience? A drop. How is it signified? With a minus sign. I'll tell you what I'm talking about. For now, just hear me out. Whenever you're traveling from negative to positive, what are we doing? Something is at a lower potential, we're going to a higher potential. What are we experiencing? We are experiencing a gain. How is it represented? It is represented with a plus sign. Again, I'm taking the example of this loop. In this mesh, if let this potential be V. If I'm traveling from in this direction, I'm traveling from negative to positive. When I'm traveling from negative to positive, what am I experiencing? I'm experiencing a gain. What will I write? Plus V, right? Again, coming to this resistor, I am traveling from positive to negative. Why is it positive? Because current is entering the element. If current is entering the element, what will we do? We'll assign a positive sign here and a negative, because current will be leaving at this point, so we'll assign a negative point here, right? Now we're traversing. Now when we're traversing, what will we see? We're traversing from positive to negative, right? We're traversing from positive to negative, right? So when you're traversing from positive to negative, what will we experience? A drop. Which how will we signify it in our? How will we denote it in our loop equation? It will be minus I1 R1. Again, this time the current is entering from this direction. I'll tell you why we are considering this to be more prominent. I'll tell you in the next step. Okay. For now, just write it. I1 minus I2 times R3 is equal to 0. So this is how we denote it. Okay. Now, uh, whichever loop we are traversing, this is what I was talking about. I said I'll explain you again. So, uh, whichever loop we are traversing, first, say this is the loop that we are traversing. So, in this case, if we are traversing loop number 1, if we are traversing loop number 1, for you know, if we are traversing loop number 1, what will we do? We will take I1 to be greater than any current, and this is why what we did, we wrote I1 to be I1 minus I2 in this branch. I'll write it down and then I'll explain you again. I1 is whichever loop we are traversing, for that loop, the current of that loop would be greater than any other current. Am I clear? See, for loop number 1, this is loop number 2. For loop number 1, see, can I write it as V? I told you why it is plus V, because we are traveling from what? Negative to positive. What will we experience? We'll experience a gain. Why will we experience a gain? Because we are moving from negative to positive. So we are gaining something. Only then a negative value can be converted to a positive value. So we are gaining something. So how do we represent a gain? With positive sign. In this resistor, what will I write? Minus I1 times R1. Now, what did I say? This current will be greater than any current. So, can I write, what will be the current in this branch? In this branch would be the difference between the two currents. See, the directions are what? Not additive, they are what? Opposite of each other. See carefully and then you will know. This is what? I1. This is how I1 is traversing. Travel in this loop. This is how I1 is traveling. And see, this is how I2 is traveling. I2 is flowing from, from this point to this point, and I1 is traveling from here to here. So, how will I write? There should be a difference between the two currents, which would be I1 minus I2 times R3. right? Equals to what? 0, right? Now tell me, now in loop 2, what will you do? In loop 2 we'll write again, this time again, whichever loop you're traversing, what will we say? We'll say the loop current is greater than any other current. So if I have to write the equation for this loop, tell me how will I write? First tell me what will be the sign here. First thing you will do whenever solving a question on KVL, will assign symbols. So the current direction of current is taken to be what? Like this. So it is in the direction of current. Whenever in the direction of the current is entering an element. See, the current is entering an element. What sign will you assign? You will assign a positive sign. The current is leaving the element. You will assign what? A negative sign. Am I clear? So we have assigned the. This is for this loop. Please don't get confused. This marking is for this loop, right? Right? So this is what? Plus, this is minus, this is what? Plus, this is minus, because current I2 is entering from this direction and leaving from this direction, so plus and minus. So now this time tell me, will it be I2 times R2, right? Minus, tell me, this time again I2 is greater than any other current, so can I write I2 minus I1 times R3 is equal to what? 0, right? Right? So these are the, this is what is called basic, this is the basic mesh analysis. There is nothing new that you've learned so far, but please be sure these are your basics. These are something that will help you. If you are very clear with the concepts right now, it will help you in the long run. Okay. Okay. Is it there is no compulsion in the direction of currents that we assume. It is just our assumptions. You can just take this. For now, it is what? It is clockwise. You can also take it anti-clockwise. It is strictly up to your choice. But be very clear with what? Sign assignments. In the direction of current, whenever the current is entering an element, you will assign it a positive sign. Okay? Whenever current is entering, whatever the direction of loop you have taken, whatever the direction of it, can be clockwise or anti-clockwise, make sure you don't make this mistake. And yes, again, see, this assignment is true for this loop. This may not be true for this loop. In this loop, what? Here will be positive, here will be negative. So assign accordingly. Assign accordingly. Okay? Right? Okay. For now, I'm assuming we're through with this topic, and I'm moving on to the question based on mesh analysis. And it's again, this is not a basic mesh analysis question. It is what? It is a question where we observe, and we in generally call it what? A question based on what? Super mesh. There is a concept of super mesh in this question. Okay. So what is a super mesh? Tell me. See, just by observation, when you see between two loops, there is an ideal current source. There is what? An ideal current source. Just by observation, when you see an ideal current source between two loops, then the simple laws of mesh analysis will not apply here. Okay? So how would you approach such questions? Otherwise, I think we're through with questions so far. So far, we've done a lot of mesh analysis, and also in our previous lectures, also we did a lot of questions which we did not do by the name of mesh analysis, but we have eventually applied mesh analysis. We have eventually applied KVL and Ohm's law, so that in itself completes mesh analysis. But a, a typical mesh analysis would not apply, in which case whenever you see what an ideal an ideal current source between two loops. So this is our question for today. Observe it for once, see the values which are given to you. The first thing, the step number one, what we do is mark the number of what? Currents, right? The first thing that we do is what? Mark the number of meshes or loops in this circuit. In such questions where there is an ideal voltage source, ideal current source, what we do, we make a, this is what I was talking about. Did I not tell you? I'll tell you the difference between loops and meshes. So this is what? This is a loop. Okay. The first thing by observation in such questions, the first thing by observation, what do we see? The first thing that we notice is, what is the current in this branch? It is already defined to be what? 7 amperes. Why is it 7 amperes? Because in series there can be only one value of current. So whatever assumption of current that we take in this branch, what would that be? That would be 7 ampere. But going by our mesh analysis, what is the current in this branch? Can I say the current in this branch is, this is what? I1, this is what? I1, and this is what? I2. I1 flows from, say, let me mark this as A and let me mark it as B. I1 flows from what? I1 flows from A to B. If I1 flows from A to B, the current I1 flows from what? A to B, right? So, but I2 flows from what? Follow this loop. I2 flows from B to A. What is the effective direction of current? Although the effective direction of current is from A to B. So can I without doubt say this is I1 minus I2 given to be what? 7 amperes. Right? Right? Okay. For example, what if the direction of current was like this? Can I still write I1 minus I2 is equals to 7 amperes? Would that still be true? No. No. In this case, what will we write? In this case, we will write I2 minus I1 is equals to 7. If the direction of current were this, we need to understand what is the effective direction of current which is already given to you. So you cannot change the directions, right? Right? So you need to be alert at this point. Okay. So this is one equation that you will get right away. Whenever you observe an ideal current source, make an equation in relation to the currents given to you. Okay, so that will form your first equation. Okay, how will you get the second equation? The second equation you get by traveling the outer loop. By traversing what? The outer loop. Now, how will I write it? Tell me. This is what and again I'll tell you what I'm talking about. See, in this loop, what will I write? Plus 10, you're traveling, I1 is traveling from what? Minus to plus, so there's again, what will I write? Plus 10, right? Minus 3 times I1, right? Minus. This time in this loop, What is the current here? I2. What is the current here? I2. So what will I write? Minus. Again, the sign would be plus. This would be minus. This would be plus. This would be minus. This is plus. This is minus. Right? So you'll bypass this branch. You'll directly reach here, and this time the current will be of which is of the second mesh. Okay. So what will I write here? Minus 1 times I2. Again, I am completing the loop here. Equals to what? Equals to 0. Equals to 0. So, can I write this equation to be? Can I rewrite this equation to be? Look carefully. 3I1 plus I2 equals to 10. This will be your second equation. Now, you have two equations. You have two variables. Can you solve it easily? I1 minus I2 is given to be 7. 3I1 plus I2 is given to be what? 10. Let's solve this for ourselves. This is what? 4I1. 4I1 is equals to what? 70. Or I1 is equals to what? 1 by 4 amperes. Can I write it as 4.25 amperes? Right? Right? Now if I replace it here, 1 by 4 minus I2 is equals to 7, or I2 equals to what? I2 is equals to 7 minus 4 1 by 4. What would that be? This would be minus I2, sorry. I've taken this to be here, right? So this minus I2 would be 2 3 by 4, or I2 would be what? I2 would be equal to minus 2 3 by 4 amperes. So this is your answer. So it is a very easy question. It is what? It is a very easy question. For today, what will you do? Today sit and repeat all the questions we have done so far. Repeat all the questions we have done so far using what? Mesh analysis. You'll encounter difficulties doing it, because that is how, and why I'm telling you to repeat such questions, because you will only when you attempt questions using various ways, you will realize, and you will have this expertise to observe and tell which method is more likely to be used, right? Right? See, here is the question. Was this the question that we were doing? Right. So, tell me for now, I'll just repeat this for you. Let's do it by another method. And what is another method? Let us do it with what? Nodal analysis. And then you'll see which method is easier. Okay. So, this is the question that you were given. This was the question that you were provided with. Look closely and tell me the step number 1. The step number 1 of nodal analysis. Why I am repeating this question using another method for you? I am repeating this because you need to understand why a certain method is more easy for solving certain questions. In this question, I want you to understand why a certain type of network is easier to solve using nodal analysis, and why a certain type of methods are easier for using mesh analysis. Tell me, the first step is what? Identify all the nodes, right? Travel from what would this be? This would be plus 10 volts. This would be what? Plus VA, and this is again 0. This is again 0 because this is not a node, it is already defined, right? Right? So, give me a second, just give me a second. हाँ 0 0 हाँ okay, so where were we? Okay, so we were trying to solve the same question which we have done using mesh analysis, using what? Nodal analysis. Now, so we clearly see there are two nodes which we have already defined their potential to be what? Plus 10 volt and VA, right? So, applying KCL at node A, observe it carefully. Can I write? See, all we need to do is write all outgoing currents. So, for outgoing currents, the current would be, the higher potential would be VA. So, can I write VA minus 10, VA minus 10 divided by what? Divided by 3 plus the outgoing current in this branch is what? 7 amperes clearly. So, we don't have to, do anything. In the next branch, what will I write? VA minus 0 divided by what? 1, right? Equals to what? 0. The sum of all outgoing currents is what? 0. Multiply the entire equation with what? 3. What will we get? VA minus 10 plus 7 3s are 21 plus 3 VA equals what? Equals 0, right? Or can I say 4 times VA is equal to what? 4 times VA equals to what? Minus 21 plus 10. Let me rewrite it. It is very clumsy. Okay. So VA is equals to minus 11 by 4 volts, right? So now we have VA. Can I calculate I2? Tell me what is I2? I2 is flowing in this direction, right? And this is what your I2 was. So can I calculate I2? I2 is equals to what? VA minus 0 divided by 1, right? So I2 is equal to what? VA. And what was VA? VA is minus 11 by 4. Can I write minus 11 by 4 to be minus 3 by 4 amperes? Just see the previous slide. What did I calculate I2 to be? Minus 3 by 4 amperes. All I am trying to say is it is completely your choice to pick a type of network that you are solving. Like this could be mesh analysis or this could be nodal analysis. It is completely up to your choice. But generally, wherever you see a current source, in a branch and you see a node close to it, it is usually preferred to have nodal analysis, and that is why I asked you to do this question using nodal analysis, because there was only one unknown, right? So usually it is preferred for using nodal analysis, but it is completely your choice. If you're more comfortable with mesh analysis, you can opt mesh analysis. All you need to understand is once you solve a lot of questions, you'll get this insight of which question to attempt using which approach. I've explained each and every KCL and KVL approach to you, and it is now upon you to pick up your favorite method of analysis. Okay. Tomorrow we'll try and finish equivalent circuits. What with equivalent circuit I mean, we'll try and understand what is star and delta, and we'll try and solve a few more questions on series and parallel connections. Series and parallel connections are, it is a very basic topic, but it confuses a lot of people, and because it is very difficult to find equipotential points by, sometimes just by, general vision you cannot just judge and tell if it's equipotential or not. So tomorrow we'll, do series and parallel. We'll try and do voltage division and current division rules, and I think that would make it all, parallel connections. Yes, that would be everything in your basic. That is the maximum basic that we'll be doing so far. Okay. I'll try and bring up a few more, questions based on your past year questions of NET and JRF. And let's see if we have more variety there, we'll solve such questions also. Okay. Okay. That's it for today. See you all tomorrow at 7.